Have you ever wondered how we calculate the rate of change for complex functions? Like when one variable depends on another that depends on yet another. Or how to find the best possible value, maximum profit, minimum cost, or fastest time. In this video, we'll unlock two powerful derivative tools, the chain rule and the quotient rule, and then see how they come alive in real-world optimization problems. Let's start with the chain rule. Look at a chain reaction with three gears that turn at constant rates. Changing angle X changes angle U, which then changes angle Y. The chain rule tells us how to find the change in Y with respect to X. That is, dy over dx, if we know the value of du over dx and dy over du. To find that, consider a point P, where the gear makes contact with a radius Rx. This point moves at a constant velocity v. The distance P travels, that the arc length is equals to Rx times x. Now, for small rotation delta x in time delta t, the velocity v, related to these quantities as v equals to Rx delta x over delta t. Now, since the velocity of point of contact is same for each gear, we get corresponding results for the other two gears. Rearranging the equations, we find delta x, delta u, and delta y. To find the value of delta y over delta x, using the above relation we need to do some simplification, and we get the following expression. For infinitesimal small change in time, the derivative dy over dx is equals to dy over du times du over dx. We showed this idea with gears, but this result holds whenever we have an intermediate variable. To be precise, the chain rule lets us find derivatives of function composition. Putting gx inside of fx gives us a new function, f of g of x. That lets us formalize our result. Derivative of f of g of x equals to f dash of g of x times g dash of x. For better understanding, let's solve one example. Consider a function h of x equals to x cubed minus 2x raised to the power 4. To find the derivative, we can consider g of x equals to x cubed minus 2x, and f of x equals to x raised to power 4. So, our function, h of x, becomes f of g of x. Now, using the chain rule, derivative of h of x is f dash of g of x times g dash of x. After evaluating and putting the individual function's derivative value into the above formula, gives us the value of derivative of h of x. Next, we will look at the quotient rule. To start thinking about quotients, let's consider a non-zero smooth function g of x. We'll find the derivative of its reciprocal, that is, 1 over g of x. We can get the reciprocal by composing g of x with f of x, where f of x equals to 1 over x. So, now we can write f of g of x equals to 1 over g of x. That means we can use the chain rule to find the derivative of 1 over g of x. To do that, we first need to find the derivative of f of x by using power rule. After applying the power rule, we get the derivative of f of x equals to minus 1 over x squared. Now we can find the derivative of our function, 1 over g of x, using the chain rule. After applying the formula, we get the derivative of our function, equals to negative g dash of x over g of x whole square. Now let's consider the quotient of two functions, f of x over g of x. We can also write it as f of x times 1 over g of x. Using the product rule in this function, and the derivative value of 1 over g of x, we can evaluate the derivative of our function. After simplifying the expressions, we get derivative of fx over gx, which is equals to gx times f dash x minus fx times g dash x, whole divided by g of x squared. Now, we have know all the derivative rules. Let's take a look on all of them before we solve an optimization problem. Imagine you run a drone delivery service. You need to design a rectangular shipping box to deliver small items. The volume must be exactly 2,000 cubic centimeters. But here's the twist. Because drones struggle with air drag, your company charges shipping based on the surface area of the box, plus an aerodynamic penalty. So, the total shipping cost is equal to material cost plus drag penalty. Let's assume that delivery box has square base of side length x and height h. Given total volume is 2,000 cubic centimeter. We can write height h in terms of x. To define our cost function, we first evaluate the material cost. The material cost is function of surface area of the box. And the total surface area is equal to 2x squared plus 4xh. Replacing the value of h, we get total area 2x squared plus 8,000 over x. Assuming the cost per centimeter square is equal to $0.50. The material cost, C1x, is equal to following expression. The aerodynamic drag penalty charged by the company in terms of box dimension is given by this expression. Replacing the value of h in terms of x, we get drag penalty cost function, C2x, equals to 6 into 10 raised to power 8, whole divided by x raised to power 6. So, the total cost function is equal to the sum of both cost, which is equal to this expression. Now that we have our cost function, we can find the value of x that minimizes the total cost by finding the derivative of this function. Using the different derivative rules and putting c dash of x equals to 0, we get following expression. Now, this equation cannot be solved analytically. So, by using the numerical methods, we get approximate value of x equals to 16.8 centimeters. And the corresponding h, that is height of the box, will be approximately 7.1 centimeter. Hence, we find the minimum cost occurs when the base side length is about 16.8 centimeters, and the height is 7.1 centimeters. Also, if we plot the cost functions with respect to x, we can see the minimum cost occur for the x equals to 16.8. Any smaller box increases drag, and any larger box increases material cost. Thus, a simple drone box leads us to all derivative rules. Now that we have learned about derivative formulas, in the next video we will start working on integrals. Thanks for watching, and I will see you on next one.